Yes, yes. Okay, we'll start with. So I'll just record it for those who are not there. Tomorrow we have lab and tutorial on clustering. You'll do two interesting problem. One is real life and you'll code it up. Monday is a quiz for those who didn't give. Tuesdays is examples and Wednesday is holiday. So Thursday I'll do a real life problem and we'll also go over your survey. But that's the thing. Coming back to this distance-based clustering. So yesterday we talked about scatter, which by now you would have understood. You'll practice more in the tutorial tomorrow. But what we are after is, rather than the scatter matrix, we are more interested in the scatter, which is the trace of the scatter matrix. And another way of writing that is this, that for every data row, how far it is away from the mean values for all the dimensions, and you add it up. Now, the point is, how would you go about building an algorithm around it, right? So the very first thing which I told yesterday was that you should have an idea of how many groups you want to put the data into, the number of clusters. If you have no idea, the heuristic says do it from n by 2 to 2, that many, and find a metric which says this is a better clustering, this is a bad clustering. So that metric we want to see today. But in terms of the algorithm, how it should proceed is, it should try to minimize this guy for every cluster it's creating, correct? This is the within cluster scatter that we are talking about. Similarly, there will be a between cluster scatter. We want to increase that one and reduce this one, right? That is what we had talked about yesterday. So if you look at this summation xi minus mu, you want that every data point be as close to the mean value as much as possible. So that brings us to the heuristic of starting an algorithm, which is the k-means algorithm, and we're going to start about that. So how that goes is, so this is an example which is given to you. So the circled points are the data points here, and now we have to start somewhere. We have no idea which groups they belong to or which they don't belong to. The only thing we have been given is that k is the 3k is equal to 3 is the number of clusters or group we have to put into. So the algorithm or the heuristic algorithm, it says it's a heuristic because it's not exactly minimizing the scatter at this stage. We don't know the groups, so we don't know the scatter, so we don't know the, how to minimize it. So we don't know what are the means. We have no idea absolutely. So we start with any three random points. So in space, you give any three random points which are given with the triangle, the tilde and the star, right? Now what the algorithm does, it tries to minimize the scatter. What it does is, for every point, the circle point, it tries to find which mean, this randomly initialized mean, is closer to me. So if you look at this figure, you can guess that these 2 points are probably closer to this, or these 2 are closer to this, these 3 are definitely closer to this, and these 6 are closer to this. So that is the first step it does. It tries to partition the data point based on the randomly initialized means. Why randomly initialized? Because we have no idea how the points will be clustered. So we start somewhere. So we do that. So you cluster created by associating every data point with the nearest mean. So this is how the Voronoi diagram will work. Voronoi diagram, remember, we had to find the distance between and partition it with the perpendicular line. So we realized that this point was closest to this. These set of circles were closer to the triangle, and these set of circles were closer to the tilde values. So we do that. Now what the algorithm does, it got a handle to the starting point. At least you got some rough clusters. Now it says, given the points, find their means, right? So if you look at the first cluster, what will be the mean value for that? This cluster, it will be this only, right? There is only 1 point, so this will become the mean. So the first mean will shift here. Then if you look at these set of points, 1, 2, 3, 4, 5, 6, and you try to find in a two-dimensional space, assuming that this is two-dimensional, right? This is not an n-dimensional space. Then where would the mean value shift? Mean value will shift where it's closer to the larger number of points, right? So these are 4, I'd say this triangle will slightly move down. It may not exactly overlap the circle, but it'll slightly come down. And when you look at this partition, there are 2 here and 3 here. So it means that this guy would slightly go up, correct? So you first initialize with random means, find and make 3 clusters and find the means of this new clusters. So once you do that, this is how the means will move out. So this guy will come to this point, this will move slightly down, this will slight move down. Now what the algorithm does, algorithm is iterative in nature. Now it says now you got 3 new means which are carrying some problem properties with it because it is coming out from the points itself. Now associate the closest point to this again. Basically try to minimize the within cluster scatter again, correct? So once you do that, you realize that these 2 points now become closer to this, these 4 points become closer to this, and these points, they remain closer to this. So now your Voronoi tessellation or the partitions slightly move. Is it clear? So it is at every step it is trying to bring some more of problem property and minimize the between cluster scatter, minimize the between cluster scatter. So in this way the mean value will keep shifting. When will you stop? When you realize that the mean values are not shifting too much, which means that now this is the ideal, it's the minimum value. Now you've figured out the mean where the distance from every point to its center is minimum for this cluster. It cannot be reduced any further. Make sense? So this is basic k-means which you learn every time. Why k-means? Because you're doing k cluster. Y means because you're using mean value to figure out which cluster it belongs to and which it does not belong to. Is it okay? Everybody comfortable? Okay. So now I think this is what is written in words format. So the k-means clustering in a pseudo format is given like this. So your input is d data points with the d small d dimensions. Capital K, it's saying the number of cluster and you want to give the mean values of them. So the first step, like we said, because we have no idea, we'll randomly initialize some points mu1 to mu k. And the algorithm is very sensitive how you pick up the initial points. So if you don't pick the right one, you may converge to a wrong, you may not even reach the right convergence, which we'll show with an example. An analogy to this is solving the Newton's method, solving a non-linear system of equation fx equal to 0 by the Newton's method. Do you remember from your second year numerical methods? What does the method go? What's the equation for that? You work with the prime, right? So you say x new is equal to x old minus fx over fx prime. So there also, to start the algorithm, you have to start with the initial guess x naught, remember? And the algorithm is sensitive to the initial point, that if you don't smartly pick the initial guess, it may not find the right 0 or fx equal to 0. So the same idea is here, so you can remember it that way. So now repeating, there is a for loop. Assign each x to argmin dis2. What is this guy doing? Can somebody tell me? Computer science people can tell more easily. What is argmin? It's the argument which minimizes the function. Argmin is nothing, so don't, it's like a normal minimization problem. Arg means that where we are after the argument which is going inside the function rather than the function itself. So it's saying assign each x to arg min j distance x to mu j. So every mu you find every point to this, to every x you take and find its distance from all the mu's, which we did in the first step. No, 3 points were there, so every one, and then we assign it to that where it's closest. So arg min j is saying the j cluster, assign it to that cluster where the distance is the minimum. Everybody okay? Now what do we do? Once we have done this assignment process, we go from 1 to k. So this is done for all the points. So this step is done for all of them, then only you go forward. Then you look at all the clusters and you find which point has gone to which cluster. So you get these 3 points here, 2 points here, 2 points here. And what do you do here? mean of the new cluster which you have now just found. And then you repeat, because new means have come, again assign, again form the new mean, again assign. So it's just repeating that. So the reason I'm spending time, because if you're non-CS, you get intimidated by pseudocode. So don't get, है ना? It's very straightforward. Okay. Okay. So K means clustering. Now this example is good. So we'll see how this is proceeding. So in this example, I'll zoom it up on each side as we go along. So the point it's saying there are 30 points. Yeah. All the data points. The small d is the dimension of the data. So it's a two-dimensional data. We have drawn it here. But typically, you will not work with two dimensions. K is the number of clusters you're doing. I'll come to that. Come. One for you, one for him. Some questions are coming. So best values ऐसे choose होती है. Like I said, you would have no idea. उसको भी दे दो ना. क्या आएगा वो? So best value कैसे choose होती है? You start from, like I said, you will have no idea. So heuristic says make 2 clusters to n by 2 clusters. You don't want to make more than n by 2, because then the points will start getting repeated. Imagine there are 10 points. So you will make 2 cluster, 3 cluster, 4 cluster, 5 clusters. You want to do 6 cluster, then it will be almost like some information will repeat. है ना? So you make 2 to n by 2 cluster and you check which clustering is better. Now, how do you check which clustering is better? I'll tell you towards the end of the class. There are many metrics to do it. One metric is called the Silhouette value, which we typically use. So we'll show. So, but there are many other metrics to tell whether the clustering is good or not. So once you compute for every cluster these value and say, okay, I'm getting the best value at this clustering, basically where you are minimizing the within cluster scatter. It is something like that. And maximizing the between cluster scatter. So that idea has to come forward. Is that okay? Okay, so let's try to take a look at this. How many of you have a class at 3:30? Oh, all of you have. Is it a CS class or no? Computer vision. Where? Oh, is it? Was Surya is teaching? Okay, I want to finish this today and see how it goes, because we lost 15 minutes to start. Okay, never mind. So D is the total data points, small d is the dimension, K is the number of clusters. And now let's look at the very first figure. I'm going to focus on, scroll, ऐसे होगा क्या? चलो, class इतनी बड़ी नहीं है, so you should be able to see. So ignore the right to, ignore these two, है ना? Just focus on this. So these are the points given to you, the pluses, correct? And the pluses are color coded to tell you that these are the actual clusters they belong to. So this is kind of a labeled data. This is counterintuitive. This is for the sake of instruction, that we already know they belong to these clusters, because we are telling you how well the clustering is working. We want to check that. You know? Otherwise, in real life, you will have no idea. It's unsupervised in that sense. So what happens is you randomly initialize 3 centers. I don't know whether you're able to notice this. There's a dot here, there's a dot here, and there's a dot here. So now what will happen is, this is the first place you initialize, and then you say which points are closer to me, figure it out. So this will be checked with all the points. This will be checked with all the points. This will be checked with all the points. That's the first step of the algorithm, correct? Now when you do that, you realize that only these 2 points are closest to this. You realize that these set of points are closer to this, and these set of points are closer to this. This is the step. So then you get this Voronoi tessellation. This divided, this divided, and then there's a line for this guy. Correct? Now what happens? You have the first clusters, you find the new means. Correct? So the mean of this and this eventually turns out to be this. It somehow comes to be here, which is this guy. The mean of all these values, 3 greens and this red comes here, because the red are more that side. And when you take this blue and these many greens, it turns out to be here. Now what happens? You again find which points are closer to this, this and this. Once you do that, you get this Voronoi tessellation. Is that okay? So this is how it's proceeding. So when you go to the middle graph, this is your starting point for this, which is this dotted line. And these black points are the purple points in this figure. This, this and this. And then what do? You again find the mean of the clusters you're in. So these were the cluster points. You find a mean, it comes here. You find a mean, it comes here. You find a mean, you comes here. And again, now you found new means, again do. So you'll keep iterating, correct? So you'll see how these Voronoi tessellation are moving. When you go to the last figure, initially you saw it was very different from this. This got slightly closer. Now you say it's moving very little, which means that the mean values are moving very little, which means that you're converging to a ideal clustering. Is that okay? Can everybody see? Okay. This is what all is written here, which I just told you. Now coming to what is K-medioids clustering. Okay, somebody tell me what will be K-medioids clustering. It's my phone. One person. I could still didn't answer your question on outliers on SVM. I'm sorry. But I'll tell you before we finish. Next Thursday, I'll tell you. So she had asked how we identify outliers if the points are going inside the soft margin. But I couldn't find a way to figure that out. So that's why. But I've not given up. I'll tell you by next Thursday. Okay, tell me, how will you do it? If it's K-medioids, what will change in the algorithm? Computer science? Correct. We'll have to find the data point within the points which is closest to all. Remember, that's the only change we do. So the algorithm, how it changes? Come. What's your name? Arya. So you missed a chance. I gave you a chance for a chocolate. Yeah.
So in the K-mean clustering, what about the points which will be equidistant from two means?
Yeah, well then you use a tie break. You use any of them. There isn't any general. Okay, so like, what's your name? Sorry? Aryan. So how Aryan answered? So let's take a look at this. So what we do, data are the number of clusters, distance metric, K-medioids. Now instead of random means, pick points within the data points as medioids, representative points. That same thing, assign to them to that cluster where the distance from that medioids is minimum. Exactly. Then once you pick all the cluster, now you're doing this, that you're finding distance of every point to every point, and where it's minimizing, you're adding it. This we'll do in an example. If it's intimidating you, don't worry. We'll do it in example tomorrow in tutorial. It will be clear to you that every point you'll have to check with every medioid, and the sum of that distance where it's minimum, that is where you would do. So that's where there is a sum. So that group it would belong to. We'll do this example tomorrow on a real life problem on the plant genetic data, which I said we used in a research. So we realized we have to use K-medioids rather than K-means because the data was not numeric there. Okay, suboptimality of K-means. So what this figure is saying, that if you don't start with the correct guesses, now if you had started with this, you may realize it converges to a non-optimal setting. So basically it's just saying that it will not be as good as the one you saw earlier. This is the stopping point of the algorithm. In the earlier you saw the changes were very minimal. It was like this, and then it just changed like this. The means were changing very little. But if you start at the wrong place, then you're gone. So that starting is important. Okay. Scale sensitivity. Okay, so this is kind of the second drawback of K-means. Now you look at the two figures. I want to finish 3:30. If I'm going too fast, then tell me, stop me. So if you look at the two figures, you are given which clusters they belong to because you're color coded. So this is labeled data given to you. It's testing the algorithm. So you check, you know that this is one cluster, this is another cluster. If you are, and this is the scale. This is this focus on the scale. है ना? Now, if you did k-means on this, it will say this is the cluster, give you this mean, this is the cluster, give you this mean. So, which means that k-means worked fine. Assuming that you initialized it correctly, which is always a challenge, right? Now, if you look, what's the difference between the two figures? Can somebody tell me? The scale is changing. You multiply this by 20. So this will become 4, this will become 3, this, and so on and so forth. So you see just the scaling of the data points has changed. Correct? Although the distribution is the same, but the scaling is just changed. Now then you apply k-means, it founds the centers like this. Basically it says this is one cluster, this is another cluster. Which means that k-means is not good at capturing the shape of the cluster. So that is what I have written in the next slide. Let's read it. So an important limitation of clustering methods is that they represent clusters only by means of exemplars. We are only after the mean value, which is a numeric value. It is not taking the shape of the data in its construction. This regards the shape of the cluster, sometimes given to counterintuitive results. Nevertheless, this is not actually a shortcoming of the algorithm, because the centroids in the two cases are farther. This is a better solution in terms of equation this. So what is this equation? So the equation that we are referring to is that you minimizing the within cluster scatter and maximizing. So the algorithm is not doing anything wrong. When you rescale the value, it is actually minimizing the between cluster scatter and maximizing numerically. We can't see it, but it's not able to capture the shape of the data. So to capture the shape of data, there are many other clusterings. K-means is the very basic one which you apply because it works fairly well. It's like the Newton's method works fairly well, although it is taught in second year, still it's used at many places, but there are many variations of it to improve it. So the 7 clustering.pdf which I have uploaded in the supporting material will give you an idea of tens of hundreds of clusterings, and they are divided into multiple groups. There is a big table which says what is your data property and which clustering you should pick up. If shape is something very important for you, don't pick up k-means. That is what it will say.
The first graph should just stretch, but the second one, the red dots are block now.
No, it is stretched. The points are still stretched.
So why the color reds are above?
The color is changed because earlier these points originally are different clusters and k-means found the means as this. Now when you change this, when you change the scale, of course the figure will look the same because if I zoom it up, then they'll look more farther apart, but now this is a zoomed down version of the scaled value. When you do that, it will find the cluster centers in this and say that this is your one cluster, this is your second cluster. This is what it will do. Color is one after k-means is done.
This is color assigned by
The algorithm, right? This is the original clustering color done correctly by k-means. This is done by k-means after rescaling, basically telling you I'm not doing it correctly. I'm doing it correctly numerically because I'm trying to minimize the within cluster scatter and maximize the between cluster scatter, which I'm supposed to do, but I'm unable to capture the shape of the data, which should be like this. It should still capture this. When you apply a more smarter clustering, it will be invariant to the scaling. There are many advanced ones and it will capture the shape. We're telling you two drawbacks of k-means. Yeah. Correct. That's another way. Normalizing of data in machine learning is very important, that you bring all of them to the same scale. But I don't know how you would normalize, because you would feel that the data is not too badly distributed. I mean, let's say one data point was -4 and the other data point was 10 to the power million. Then you say the variation in the data is too much. So I'll try to normalize it and bring it in one scale or do a rescaling. But here the normalization, I don't know how much it will help, because the scales are not too varying. Is that okay? What's your name? Huh? Come, take this. Questions are coming. Your name? Ayush. There's no. You already got too many, Shivam. Yeah, tell me. Different from which method? What do you mean by thresholding? Sorry? Thresholding, I don't know which thresholding you're referring to. By name, it means that there is a boundary and above a boundary it's something and below a boundary it's something. Is that what thresholding you're talking about? You talk to me after class, है ना? Is that okay? Because we'll not be able to finish this. All right, so this is the rescaling problem, and this is what I read that it is doing correctly. But so the real issue is that we want to estimate the shape. Hence, rather than just using the trace of the scatter matrix, we have to use something else which advanced algorithms do. So in case you're using a research paper which has clustering in it, you'll invariably be using a smarter clustering in that paper, because k-means is very rarely used. It's more for teaching purposes. Okay. Now before, how much time do we have? We have 12 minutes. Okay. Good. So we're running out. I'll take your question at the end, and let me finish this because it will answer his question, whose question it was, that how well the clustering is. So there are many metrics to tell whether a clustering is good or not, and Silhouettes are one of those values. What is the English meaning of Silhouette? Well, the outline of the shadow. Basically, if I'm standing here, you can draw outline on me. That's my silhouette there. है ना? So what silhouette, the meaning, English meaning will be clear in a minute. But let's try to read it first because the slide is self-evident. Then I'll explain you. So what it does is, for any data point, let dxi dj denote the average distance of x point to the all the points in the cluster dj, and let ji denotes the index that it belongs to the cluster. So what is axi? Axi is the average distance of xi to the points in its own cluster, and bxi, now I needed something to write, but there's no. Everybody can see these signs, huh? So let's say I'm this at any random point in any random cluster. So what it's saying is that I will find the distance of these points. This is the average distance of xi to the points in its own cluster dji. So I am the ith point, and ji is my cluster. So this is the first cluster. This is I am this. I will take the points of every point from this and average it out. Divide by 4. Basically, I'll find this distance, correct? And then what I'll do, I'll find the distance of this to all the points in this. I'll take this point, find a distance to all the points in this. Which one will be minimum? This one will be more closer to this than this guy based on the figure I've drawn. So which means this is my bj value and this is my aij value. That is what it's saying. What is bxi? Be the average distance to the points in its neighboring cluster, and you're finding the minimum of that. So you do it for all the clusters, and the minimum which you get is this. Now what do you want? You would want, ideally what will happen if this ai is the axi is the distance to within cluster, and b of xi is to the closest neighboring cluster, the average distance of one point. I'm talking about every point here, है ना? So now what would you expect? Will a be greater or b be greater? Ideally you would expect b be greater, but it's not guaranteed, right? Assume that b is greater. So what you will do, you will say ki bxi minus axi because it's a greater value, and then if I divide this by bxi, then I am getting a representation. If what would ideally I would want? I would want ideally this should tend to 0. or this should be as minimum as possible. It will be 0 and all points are overlapping, which will not be the case. I would want to minimize this. And then this is the distance to the closest structure. So if this tends to 0, what will be this value be? This will be nearly equal to 1. So this is a good clustering for that particular point, for one point which I picked. That if I am able to get a value of 1, this one, I am a good clustering because I am very close to my own cluster. So I'm minimizing the within cluster scatter. Although I may not be maximizing the between cluster scatter, which is also another metric, which like I said, K-means doesn't do. Most of the clustering only worry about minimizing the within cluster scatter, or the between cluster scatter is important. But sometimes what can happen, it could be that you are farther from your and more closer to the other ones. It could happen because you don't know. It maybe it converges to a bad clustering and you are more closer to the points of other cluster than yourself. So in that case, AXI will be greater than B of XI. So in that case, you would try to find A of XI minus B of XI, and then you'll say I'll divide by the larger value. In that case, I will also say that if I am 1, I am a good clustering. But this is not the ideal clustering because you are being misled. You are closer more. So ideally, you should belong to that other cluster than belonging to your cluster. Is that okay? You're ideally after this, but you would not know this because this will be done automatically for every point you will do this. So that is what is written here. So it says we would expect AIXI to be considerably smaller, but this cannot be guaranteed. So we can difference BXI as the indication how well XI is and divide by BXI to obtain the number less than equal to 1. So we're kind of normalizing it here, so you can tell whether it's good or not. Smallest dissimilarity, okay. So this is saying what I just said, it could be A of Xi is sometimes greater than B of Xi, so this will be negative. So rather than doing so what you do is, you do the absolute value. So you check whether AXI is greater or BXI, so you basically write and divide by the maximum value of this, so you get a norm of that. So you take the, so basically, okay, let's first see the answer and then we'll see. So now you look at two figures. So what's happening in these figures? Okay, so what it's doing is, these are all the data points in cluster 1 on the axis. These are all the data points on cluster 2. And then these are the Silhouette values which are obtained, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And all the points, whatever number of points they are, I don't know. So what the algorithm is saying is that you draw a boundary around it and fill it up, draw a boundary around this and fill it up. So you don't know how many points are there in each cluster, but you're computing Silhouette values for each of them. So you realize that all these Silhouette values are closer to 1. If you look at this is 0.8 to 0.1, which means that it is a good clustering. Basically, it has, if you ignore this case, whether the bad case that AI becomes AXI becomes greater than BXI, if you just focus on the correct case, you have basically tried to minimize the within cluster scatter, which means you're closer to 1, which means that it is a good clustering. If you look at the second figure, for some data points, the Silhouette values are fine, they're towards the end. But for some data points, the Silhouette values are so low. They are so low, which means that this A and B are getting closer to each other. Which means that you are equally close to yourself than to the other cluster, which means that your clusters are not compact, which means that you have not been able to minimize the within cluster scatter. Is that okay? So this is a bad clustering. This is a good clustering. I think that's it. That is what it's trying to do. So in terms of the formula, I think ideally you would put here an absolute value because you want to put this between 0 and 1 and divide it by the maximum value. Another way is that you don't put an absolute value, then the range of Silhouette values vary from where to where? Minus 1 to 1, because you're normalizing with the maximum of the value. Is that okay? Okay. Okay, I think that's it. Now coming to your question. So how much time do we have? We have couple of minutes, yeah. So I don't know what thresholding is. You have to explain it to us. Has anybody else used thresholding? Yes? Image processing. Okay, what is it? Then tell me somebody.
Image processing, we have data, this data given. So what we do is that we pick a value and define that okay, any value above this will be considered as 1 and below will be considered as 0. So this kind of.
So I mean, you can't apply a direct thresholding here because there are multiple means, like we said, no, and you can think of it related to thresholding because you're seeing the distance how you are far away from the mean. So you can think of it some sort of a thresholding, but not exactly the same because the data points are different. The distance metric can change. In this one, the distance metric, we are always using a squared 2 norm because that is the mean value which gives us the exemplar. But you can do it with 1 norm. You can do it with, not a squared 2 norm. So you can do it that way. So it is kind of thresholding, but a more sophisticated one, if I have to put it that way. Is that okay? Everybody good? So we come tomorrow. A little bit of uncertainties which are there in this part will be clear in the lab tomorrow. Your question got answered. So basically, for every clustering, you will compute Silhouette maps. Why was it a Silhouette map? Because it is creating an outline. For every point, it's creating an outline. So the K value for which you get the Silhouette map, which is filled up towards the one side, will be a better cluster.
Like area below that.
Basically you can say area. But sometimes you do clustering even for labeled data. Although this is unlabeled data, we don't know which clustering it belongs. That's why we are using Silhouette values. So in that case, there are many other. There is a randomized index. There are many other values. If you do your survey paper, if you're doing on clustering, it will probably use many more metrics. Is that okay? All right. Thank you. Two additions I wanted to talk about in the class because I didn't realize when the class ended. I realized that this you should know. And then the second thing was now that we'll meet on Thursday because with Monday is quiz, Tuesday he will do some practice problems and I'll not be there. Wednesday is holiday. Thursday is the last time we meet on a real life application, so you'll forget everything. So that's why I wanted to go over this. You guys come here now, so that you can at least, everybody else can see. Okay. So what was K means? Can somebody summarize it for me? What was K means? It was an algorithm, right? So K means was an algorithm to find the ideal cluster. How did it start? You started with random centroids or random means, and then you find which are the closest points, and then you build this Voronoi tessellation implicitly, and then when you found a set of data points, you found the new centroids, correct? So in this example, for example, we had started here. This guy had moved here, this guy had moved here, this had moved here. So lines were, they were getting closer and closer. So if this was one cluster, this was another cluster, this was kind of the third cluster, and this was another cluster. The way the centroids were moving towards the center of the points which it was finding it to be a cluster, it was making them compact, correct? So what I said in the class was that it is trying to minimize the within cluster scatter, which is correct. But if you look at it implicitly, if these clusters get smaller and smaller, let's say this gets smaller, this gets more tighter, you are actually getting away from the other clusters. So it is trying to maximize the between cluster scatter without explicitly computing it. So it's not that it's ignoring it, it's just that the minimization of the within cluster scatter on the side is giving you maximizing of the between cluster scatter. So that's one point I wanted to tell you. It's not ignoring it, although it's not explicitly computing it either. Because how did we compute the between cluster scatter? We had replaced all the points with the mean values, and then we had found the scatter of all the set. So it's not doing that explicitly, but somehow implicitly that is being taken care of. That's one thing I wanted to tell. The second thing was about the Silhouette values, which happened at the end and we did kind of in a hurry. So I wanted to clear that aspect as well. I am recording this as well. So everybody agreed that this is the expression for Silhouette value. This was Bi was the distance of that data point to the cluster which is closest to it, the minimum of the other cluster, and this was the distance, average distance to all the points within the same cluster. So this was kind of capturing the between cluster scatter, and this was capturing the within cluster scatter, correct? And we were normalizing with B or A depending on which was larger. Now look at it, how you can write it this way. If AI was greater than BI, AI was less than BI, this will be positive and will be dividing by BI, so this will become 1 minus AI over BI, correct? If it is equal, of course it will be 0, but if AI is greater, then it will be BI over AI minus 1. You can write it this way, it's just synonymous. Now let's take a look at the first case. In the first case, if you look at it, when will this be tending towards 1? When this AI is small and BI is large, correct? When this kind of tends towards 0 and this kind of tends towards infinity, then the whole thing, or not infinity, because then it will be 0 over 0, you will start thinking about L'Hopital's rule. But in general, when the numerator is small and the denominator is large, it will tend to 1. Numerator will be small when it is compact, and denominator will be large when this point is away from the next closest cluster, all the points in the next closest set. So this is kind of minimizing the within cluster scatter, maximizing the between cluster scatter. So that is why getting a value of 1 is good. Correct? So 1 is considered a really good Silhouette value, where both the within cluster and between cluster scatter is taken care of. When the two are equal, you are kind of same distance from the point in your cluster as well as the neighboring cluster, which means that you are not that good, you are somewhere in the middle, so that's why it's 0, it's not good. Look at the last case. The last case, if you look at this, if BI tends to 0 and AI tends to infinity or gets large, if BI tends to 0 means that you are very close to the points in the other cluster, and your AI is large, which means that the points from the cluster you are in is really spread out, which means that this will tend to 0 and this whole thing will become minus 1, means you are in a really bad clustering. So the spectrum of the Silhouette value goes from minus 1 to 1, where minus 1 would be a really bad clustering, that you are closer to the points in the neighboring cluster than to your points. 0 would be when you are both equally distant, and 1 would be when you are really close to the points in your cluster and far away from the neighboring cluster. So minimizing the within cluster scatter, maximizing the between cluster scatter. So it is taking care of both the things. Is it clear now? Because there was less time yesterday, I didn't spend too much time explaining this. So those are the things I wanted to tell. The third thing I wanted to tell was the survey paper. This is also getting recorded, so those who are not there, please listen to the recording. So you have, by now everybody is, I think 90% of 99% of you have shown me the papers and got my approval. Those who are showing me again, first, second conference on this in Ethiopia, first, second conference in, maybe Khandwa, something like this. So don't do those. It's nothing to do with the city. It could be third conference on something in New York City. It could be bad also. I'm not saying the city is bad. It is just that the conference number, if it is really early on, you don't know how well it is. And who's publishing is it, you don't know. IEEE has everything, like I said. So don't do that. Assuming now 99% of you have found the papers, now what do you do with it? The idea is that you would have picked papers for a problem. That's what I've been telling you. It should solve one problem. It could be a variance of the problem. So the server paper will start with a section on introduction telling what is the problem, what variants exist. So you'll summarize those variants, A, B, C, D, bulleted points or something like this. Then you will say these papers solve these variants by these models. model A, model B, model C. Why does model A work? Why B doesn't work? Why C works? C, A doesn't work. So that kind of an argument or tussle your survey paper should tackle. Then you'll come to the results. Then you'll say, okay, this guy is not tested on a real data set, did on a smaller data set, it did on this, it didn't do that, something like a pro and con analysis. So those are the sections you will summarize, and you will tell what is good about it or what's bad about it. So that will help you get inside the depth of the paper. That's the idea, that you understand the paper well and write it in your own words. Don't use chat GPT and I summarize it for you. And although it does a good summary, I know you'll be tempted to do that, but do it yourself. Or even if you do it, change it, do your own handwriting. You don't have to do it in LaTeX, you don't have to replicate the code, you don't have to run the experiments, you can do it in Word. We would need just a PDF submission. The deadline I'm keeping it is 17th March, which is the day you come back after the break and start with Chandresh, so that you finish by then. I don't want to load you when he starts giving assignment for the lab. Is that okay? Next week we show you quiz marks. Like I said, I'm going to curve it if the numbers are really low. We are right now grading, we are checking how many people have got 10 out of 10. So then I'll come to know that whether you are missing and not done all 4 problems, if there are a lot of students who have done it, then probably I cannot curve. But if there are majority of them who are failing and not reaching all 4 problems, then I'll curve it. So that I'll give you. And then, yeah, I think that's it. Thank you.